Okay, yes, let's confirm. Great. So welcome everyone, welcome to our session. I hope you are well and you are having a great week. So today we will make an introduction to evaluation, and let me just go over the slides. Okay, in the past few weeks we were discussing data preparation, data modeling, model building and evaluation. We briefly make an introduction actually during our workshop this week. So we discuss accuracy, we check models, correct predictions on the training data and on the test data. We check the percentages and compare actually decision trees with SVM. So we made a very brief introduction to model evaluation during our last workshop. So today we are going to discuss some of the other evaluation techniques, and during next week in the workshop we will discuss these and also implement some of them. Okay, so let's remember what we were doing in the model evaluation. This is actually one of the most important steps of CRISP-DM framework. We check whether model achieves the aim we set at the beginning. So the main idea of the evaluation, actually there are two things. We compare the models, since we built several models, and then we compare them to decide which one is the best for our case. And also we check whether the model can achieve the initially set objectives. For instance, initially, if we set an objective identifying fraudulent cases with 80% of, let's say, accuracy, during model evaluation, we check whether we can achieve that particular accuracy. If not, if you can't achieve the target, then maybe we need to go back and fix even data preparation. Maybe even we need to collect more data to achieve the initial set objective. Okay. So they are very important. They actually key measure to identify the model performance, and we perform model evaluation on the test data. Okay, so as you may remember, we partition our data to training and test. Training used for model building, for the learning, we learn from the data, and test is unseen. We keep test data to the last stage, actually evaluation stage before deployment, to see whether the model achieves our objectives or not. So we apply evaluation techniques on the test data. And so we discussed accuracy during our last workshop. Today we are going to discuss some other techniques. We will mainly focus on confusion matrix, and we will discuss ROC chart. I don't think we will have enough time to cover all, so we will continue during the workshop to discuss the rest of the evaluation techniques. Okay, so let's start with the confusion matrix. Confusion matrix is like a summary table. It compares our predictions versus the actual target value. So I'm going to discuss the concepts over an example today. We will mainly focus on churn prediction. Let's say we have this company, their customers are leaving, so churning, and we would like to predict those customers who are going to leave so that company can actually try to keep those customers as a business strategy. So in our target variable, we have churns, not churns. And not churns. These are the categories on the target variable in the dataset as we discussed last workshop. So in this particular case, yes means churn. So these are the yes cases. In the dataset, let's say they are denoted by yes or no. In our workshop, churns were denoted by 1 and not churns were 0. So in this case, assume yes means customer is a churn, left the company, and no means customer is still with the company, didn't churn. So confusion matrix actually helps us to get the summary, overall summary of our predictions versus the actual outcome. It can give information about the two error types. This is quite important. We call them type 1 and type 2 error. Let's start with the type 1, which is known as false positives. So these are the cases we predict as a churn, but actually they stay. So we raise a false alarm. We inform the company, these customers are going to leave. Please focus on those, but actually those customers are going to stay. So it is a false alarm, and we call it as type 1 errors. Okay. And this is the example. And the second type of error is type 2 errors. These are the cases where we fail to raise the alarm. So the model predicts the customers as stay, but those customers are going to leave actually. We missed those customers. It's a missed opportunity. We failed to raise the alarm. And we briefly discussed these cases in the previous workshop. So when we make an error, there are different types of errors, type 1 and type 2. Type 1 is false positives, where we predict as a churn, but they were actually stay customers. They are not going to leave. And false negatives are the ones we predict as a stay, but they actually left. So these two errors have different implications for the companies. So let's discuss this confusion matrix in more detail over this example. So this is our test data, okay, this part. And this is the actual target value churn column. Okay, this is a column in our data set, and it shows whether the customer left or stay, and the others, these are the independent features, these three. Okay, so our model returns predictions. As you may remember, this is obtained from the model. We provided the test data, and model returns these predictions for the first customer. The model predict as a stay, not churn, and this customer is actually stayed. So this is a correct prediction. For the second customer, our model returns as yes, and yes means left. This customer is going to leave, and the customer actually left the company. Okay, so we can compare, as we did in the workshop, actual outcome versus our predictions. So what does it mean in terms of our confusion matrix? So as you see here, these cases are continue overall. We have, let's say here, 500 cases, 500 test records. So if you sum them up, here you will see we have 15 on the yes row, and we have 485 in the predicted no row, and overall it is 500. So overall we have 500 cases. And in the confusion matrix, we divide these cases to different groups. On the rows, we have our predictions. So this is our predictions. And on the columns, we have the actual outcome, actual target value. And yes is just to remind you churn. And no means it's a stay, not churn. So target value can be divided into two categories, churn or not. And then we denote them as yes or no, since it is in our data set in that shape. And with the confusion matrix, we have this overall picture. So predicted yes means this is predicted as a churn. And predicted no means this is predicted as a stay or not churn. Okay. So what we see from here. First of all, this cell gives an information about the true positives, our correct predictions for the churn customers. So model predicted these cases as churn, and they were actually churn cases. So this is the intersection of yes and yes. And 10 customers predicted as a churn. Actually, overall, we have 15 churn predictions, but 10 of them are identified correctly. So these are the true positives. True negatives, these are the customers identified correctly as stay. So 395 customers are identified as stay correctly out of the actual stay customers. So model predict these cases as stay, and they were actually stay cases or not churn cases. So these are the correct predictions. And then we have errors, as we discussed in the previous slides. False positives are the ones we predicted as churn, but they were actually not churn cases. So these are the false positives, 5. And false negatives are the customers we predicted as stay. So they are in the stay row, but they were actually churn customers. So we missed this opportunity. We couldn't identify, the model couldn't identify them correctly. So our predictions versus actual outcome are divided into 4 groups in the confusion matrix. 2 of the groups shows the correct predictions as true positives, true negatives, and 2 of the other groups are the errors we are making, type 1 errors as false positives and type 2 errors as false negatives. And at this stage, I would like to just quickly touch upon these positive and negative terminology. Positive is generally used for the cases where we would like to identify. So for instance, in this churn case, the business is focusing on the churn customers. So those are the positive cases we call, and negatives are the ones staying already, stay customers. In the cancer prediction, for instance, positives are the ones we would like to predict as cancer patients, and negatives are the ones as the healthy patients. So for each business problem, we can identify positive and negative class. Positive class is the one our interest. So business is interested in that particular outcome. Like if you consider the fraud case, we are interested in identifying those fraudulent cases rather than legitimate ones. Okay, positives are fraudulent, legitimate are used with the terminology negative. Okay, so you will get used to this terminology as we discussed more cases, but don't be surprised. So positive, even churn sounds like a negative outcome. Since it is the outcome of interest, we use the terminology positive whenever we would like to refer to churn. Okay. So just to summarize, confusion matrix can actually group our predictions versus actual target outcome, considering the correct predictions we are making and also considering the errors we are making. Okay. So overall, we mentioned that this is actually the summary I already mentioned. We have 500 records in the overall test set. So if you sum the rows, we have 15 yes cases as a prediction and 485 no prediction. This is no prediction. And this is churn prediction or yes prediction. And if you sum up the columns, you will see we have 100 actual churn cases in the target variable, and we have 400 not churn cases in the target variable. So we group these 500 cases based on the correct predictions and based on the errors we are making. So we can obtain these numbers from the confusion matrix. We can also obtain some other measures, which is the most useful and important part. We already discussed the accuracy in our previous workshop. Accuracy is the percentage of correct classifications, correct identifications. So it doesn't actually differentiate between churn and not churn predictions. It is overall correct predictions. Therefore, in the formulation of the accuracy, we have correct predictions at the numerator and total number of predictions at the denominator. So in this particular case, if we check our total correct predictions, 10 from true positives, 395 from true negatives, overall we have 405 correct predictions out of 500. So overall, the summation is all cases in our confusion matrix, which is 500, and our accuracy with this outcome is 81%. So let's say we built the decision tree, and this is the output of the decision tree, and this decision tree has an accuracy of 81%, okay, in terms of churn, not churn correct predictions. But there's an issue with the accuracy measure. We briefly discussed in the workshop. First of all, accuracy do not differentiate between churns and not churns. So this is the correct predictions for the churn cases, right? And this is the correct predictions for the stay cases. If we consider accuracy, we sum them up. So we don't have any differentiation. And as you see in here, the model is much more useful to identify those stay cases rather than identifying churn cases. So when we have imbalance in the data set, or if we have one particular outcome is much rare compared to the other outcome, then accuracy is not a good measure. And also if the errors have very different costs. So what do I mean here? The company don't want to miss those churn customers. So if you check this case, we predicted as stay, this is no prediction, and we missed these 90 customers. So this error is quite costly for the company compared to the false positive error we are making. So this is the error where we identified as a churn. Our prediction is churn, but they were actually going to stay. So when we have different costs for the errors we are making, and if we have an imbalance problem, accuracy is not a good measure to compare models. It can be misleading since it doesn't differentiate between different errors we are making and it doesn't differentiate between the outcome like churn, not churn in this particular case. For instance, if you consider the healthcare cancer prediction, identifying those cancer patients are very important compared to identifying healthy patients. And if you use accuracy, you don't know whether your model is successful to identify those cancer cases. So for that reason, there are different techniques we are going to use to compare models. One of them is precision, and it is actually tells us what is the proportion of positive identifications is actually correct. So I added some small notes here. I will share the complete slides after the lecture to just give you more explanation. If we consider it over the churn case, precision actually answers to this question. So of all the customers we predict to churn, so out of all yes predictions, here in total we have 15 yes predictions, what proportion actually left? So how often we were correct in our churn prediction? Precision is directly related to the false positive error. Okay, so if we consider this, in this case we have 10 true positives out of 15, and precision is 0.67, and that means when the model, in this case let's say this is a decision tree, assume when the decision tree says a customer is going to churn, is going to leave, it is correct 67% of the time. So out of all positive identifications, out of all churn predictions, what is the percentage we are actually correct? If the precision is low, so if this value, it is always between 0 and 1, if it is close to 0 or low precision value, that means we are making lots of false positives. We are identifying most customers as churners, but they were actually going to stay. We are raising too often false alarm. If it is close to 1, then that means we are quite correct in our churn identification when we make a prediction, churn prediction. The other measure is recall. Now in the recall, if I go back, in the precision, we focus on our yes predictions. As you see, we focus on the row here. In the recall, we actually focus on actual churn cases. And it is the proportion of actual churners identified correctly out of all churners. So in here, we have 10 true positives. Overall, we have 100 churn cases, and we identify 10% of them. And in terms of the interpretation, of all customers who actually left the company, what is the proportion our model identified those correctly? And in this case, it is 10%. So if you go back and think about the accuracy, where the model has 80% accuracy, now we see actual model can identify only 10% of the churn customers. So accuracy is misleading in this case. It is actually dominated by the stay customers. So the model caught 10% of the churners, but we miss 90%. And this is a kind of missed opportunity or a kind of high percentage of type 2 error. Another measure is false positive rate. Now we focus on our no predictions, stay predictions. These are the stay cases or not churn cases. And it is the proportion of it is the proportion of incorrect stay predictions out of all stay customers. So of all the customers who are going to stay, what proportion are wrongly identified as churners? Overall, we have 400 stay customers, and 5 of them identified incorrectly. So false positive rate is only 1%. And in terms of interpretation, the model incorrectly flagged 1% of customers as potential churners. And another measure that we can obtain from confusion matrix is the true negative rate. And true negative rate is now how many or the proportion of stay customers identified correctly. What is the percentage of stays identified correctly by the model? In this case, model is quite successful. We identify 99%. And as you may see in here, false positive rate and true negative rate always adds up to 1. Okay? If we have high true negative rate, if we can identify most of the stay customers correctly, that means we are making less false positive errors, or we are raising the alarm less frequently. Okay, so these are the 4 main measures we can obtain from the confusion matrix directly. Any questions at this stage? If you have any questions, please feel free to write. One question, is this accuracy we use confusion matrix to calculate the same as the Python accuracy? Yes, that's the same exactly. The accuracy, if I go back to the previous slide, we can use the version, we use core function as in the workshop to calculate the accuracy, but we can also kind of obtain that value from the confusion matrix. It is the percentage of correct identifications for both churn and not churns out of all test cases. So in this case, we have 500 case and we identify 405 of them correctly. And as an accuracy percentage, it is 81. Okay. Yeah. So another measure we can use, this is not that interpretable as the previous ones, therefore I leave it to the last slide for the confusion matrix, is F1 measure or F measure. It can be called as F1 score or F measure. This is the kind of harmonic balance between precision and recall. So if we go back and remember what is precision and recall, or maybe I can just explain here. Recall is focusing on the percentage of churners identified correctly. So here, for instance, it is about the actual churn cases. We have 100 churn cases and we identify 10% correctly. So our recall here is 0.10. Out of all churn customers, the percentage we identified correctly. Precision, on the other hand, is about the precision of our prediction. So out of all positive predictions, all positive predictions are in here, 15. The percentage of time we were actually correct. So in this case, it is 10 divided by 25. 15. Generally, when we increase recall, precision drops. So there is a trade-off between precision and recall. When we have a higher recall, we make more positive predictions. And when we make more positive predictions, there's a higher chance we can make errors, false positive errors. That's the reason there is this trade-off between recall and precision. And F1 measure is the balance in between these two. So that is the formulation of the F1 measure. And when we put these values into the equation, we obtain a value between 0 and 1. And we want F1 measure closer to the higher value, closer to the 1. So that means we are making good differentiation between, for the positive predictions, we can identify churners correctly. If it is close to 0, as in this case, it is on the lower end, that means our model is not successful identifying those churners. So we will use these measures to compare the models, and in most of the time, depending on the errors we are making, depending on their costs, we may want to have a balance between precision and recall, and if that is the case, we can use F1 measure, which is quite useful. Okay, so let's have a quick break and discuss this question. So let's say we would like to have a classification model for identifying whether a patient has cancer or not. And let's consider the errors we are making during the classification. False positive, these are the errors when the model wrongly identifies a healthy patient as a cancer patient. And false negative happens when the model incorrectly identifies a patient with cancer as a healthy patient. So this is a false alarm. It may help you to keep this on your mind much better. And this is failed to raise the alarm. So the question is, do you think these errors have the same weight or do they have the same cost? So what do you think? You can use the chat to write your thinking process or write your answer. Do you think these errors have the same weight, or do you think one of the errors is much more important than the other? Okay. I see one answer. Okay, now I see more answers. So false positive means we identify a healthy patient as having a cancer, and false negative means we miss the cancer patient and we identify them as healthy. Yes, I see several false negatives, which is correct. In this particular case, definitely background information is really important. And false alarm is also not good for the patient, since you may alarm a healthy patient as having a cancer, but you don't directly generally trust the result of the machine learning model. If the machine learning model raises an alarm, you have additional checks for that particular patient to see whether they have cancer or not. But for the false negative, so we tell the patient you are healthy, and patient didn't appear until the next appointment, and it might be too late to catch or treat the patient. So depending on the business problem, we generally have errors where they have different weights. And that's the reason accuracy is not a good measure. We need to consider problem-specific evaluation techniques. Okay. So another one. So accuracy is just one snapshot. Confusion matrix. If I go here, we get the model predictions, and then we put them into this matrix format where we can compare them with the actual outcome. So this is one snapshot. In order to understand model robustness, another technique has been proposed, which is known as receiver operator characteristic chart, ROC chart. And this is generally used where we can change our predictions based on the threshold values where we used to predict the class. So what do I mean? Let's discuss it or an example. So assume another case now. We have a marketing case, and this company is going to apply a marketing promotion to their customers, but they would like to send the promotion to the customers who are going to respond to the marketing campaign. So for instance, I sent the promotion to you, and then you use that marketing campaign and you continue to shop with me. So the company would like to identify which customers are going to respond, which customers are going to start to shop from them. And they have this historical data from the past campaigns. They see customers after the marketing campaign, whether they are continue to shop or whether they just leave. And they have this particular data. And you build a machine learning model to identify those responders. So your main aim to identify the customers to target with the marketing campaign. And in the target variable, we have again yes and no cases. Yes means this is a responder. And no means customer is not interested in, not responder. Okay. So we can directly obtain these estimations, yes or no predictions from the model, or we can also obtain the prediction probabilities becoming a responder. For instance, we mentioned that in the decision trees, we can obtain the probabilities of a yes outcome or no outcome. So our logistic regression return the probabilities. So from machine learning models, we can obtain class predictions directly, or we can obtain these probabilities. And you can obtain two sets of probabilities. They will add up to one when we have two outcomes, yes or no. Here you only see the one outcome responder probability or prediction yes case. Prediction yes probability. Okay, so these are the probabilities returned for becoming a responder. You can consider this as the chance of being a responder. So higher prediction probability means there's a high chance that customer is a responder. And when we have these probabilities, we can convert these probabilities to class predictions using a threshold value. By default, this threshold value is set to 0.5. What do I mean? If the probability you obtain from your machine learning model, probability of yes, is greater than or equal to 0.5, we predict this as a responder, yes case. If probability of becoming a yes is less than 0.5, we predict this as a no case. So here, if you check, probability is 0.7, we identify this as a yes. Probability is 0.47, we predict as a no. This is a no, and this is a yes case. So if the model returns these probabilities, you can directly change them by using the threshold value and classify them either yes or no. In some cases, models directly return these prediction classes, but we can also obtain the probabilities as in the decision trees. We can count the number of samples in a particular branch, their classes, to identify the prediction probabilities. So how we use these prediction probabilities? These prediction probabilities are quite useful to understand model robustness. So what do I mean? The confusion matrix, for instance, here we have this, for this response case, is set up with the default threshold value, 0.5. So let's have a line in here. This is for 0.5. And these prediction probabilities are ordered from highest to lowest, as you see. All over the line will be marked as, sorry, this is not, I missed the other one. Let's delete. Okay. This is 0.5. Okay. So since these are all ordered, these are the prediction probabilities. 0.6 is greater than 0.5. Our prediction is yes. This is greater than our prediction is yes, and so on and so forth. And anything under the line is predicted as a no. And confusion matrix is just one snapshot obtained with threshold 0.5. This one is a confusion matrix with 0.5. And here, let's see, this is the actual target value. This is from the test data, and this is the prediction from the model. How many true positives we have? So one yes case identified correctly, this one identified correctly, and this third one identified correctly. So overall, we have 3 true positive cases. And how many false negatives? Actually, this is wrong. Let's see. We identified, let's check for the false positives first. So how many false positives we have? We predict as a yes, and this was a no. So this is a false positive. We predict as a yes, and this is a no. So this is false positive. So we have 2 false positives here. And if we check the no predictions, how many of them are identified correctly? So let's use a different color. We predict as no, and it was a no. So this is a true negative. We predict as a no, it was a no, this is true negative. And we predict as no, but this was a yes case. So this is false negative. So we have 2 true negatives and 1 false negative. So basically, how we obtain the confusion matrix, we compare our predictions with the actual value, and then we count. But this is just for threshold 0.5. So let's see what happens when we have threshold 0.75. So now we have a line just from here. Anything above this line will be predicted as yes, and under the line will be predicted as no, since we ordered the probabilities. So all probabilities here are less than 0.75, and all probabilities here are greater than 0.75. So what is the true positives now? The actual value is yes, and we identified as yes, so this is a true positive. Actual value yes, we identified as a true positive. So we have 2 true positives. From the positive predictions, there is no error. All of them are correctly identified. Therefore, we have 0 false positives. But for the negatives, predictions, let's see. We predict as NO, and this was NO, so this is true negative. Predict no, it was NO, true negative. These 2 cases are all predict as NO, and they are identified correctly, true negative. So we have 4 true negatives, but now we miss these 2. We predict as NO, but it was a yes case, so we missed this false negative. We predict as NO, it was a yes case. We missed this false negative. So when we change the threshold, as you see, values are changing. That's the reason ROC chart helps us to see how our model is going to respond with respect to different thresholds, how many errors we will have from different types, like how many false positives we have when we have a higher threshold, or when we have a lower threshold, how many false negatives we will have. Since model performance is quite dependent on the threshold value, ROC chart can help us to see overall model performance with respect to different threshold values. And in this ROC chart, what we have, on the y-axis, we have true positive rate. So this is recall measure. You may not currently remember, but on the y-axis, we will see the percentage of correctly identified as responders. And on the x-axis, this is the false positive rate. So percentage of incorrectly identified not responders. So as you may remember, this part is related to recall. TP divided by true positives plus false negatives. Out of all responders, the percentage of them are identified correctly. And for the false positive rate, let me use another color. Out of all not responders, what is the error of being missed? What is the percentage of wrongly identified not responders? So here we see how this line changing. So let me also have another color here, the orange one. This is the model performance. For different thresholds. So what we expect from a good model to have a higher true positive rate. So a good model should be closer to the y-axis and while making less false positive error. Overall, it will be always going between 0 and 1. So it will always go to this point from the origin point. But for a good model, we want it to be closer to the corner, upper left corner. What does it mean? This model can achieve high true positive rate, or this model can identify a high number of total responders when it is making less false positive error. So as you may remember, when we are increasing our positive prediction, this is predicted yes cases, we can increase true positive rate. If I predict everyone as responders, let's say for your class, I'm predicting you all as responder. I'm going to cover actual responders in that particular class. But that means I will make lots of errors, lots of false positive errors, since some of you may not be interested in that particular marketing promotion. So in order to achieve very high recall rate, we generally make more positive predictions, but this may lead to more positive false alarms or false positive errors. So that's the trade-off actually observed in the ROC chart. And for a good model, we want to have high recall rate. We would like to identify those responders while making less errors. So let's see how this will actually calculate it. Very, very briefly, we will cover this during the workshop. We will see a small example. But what we do, as I mentioned, confusion matrix is just one snapshot. For the ROC chart, we need to see the performance with respect to different threshold values. So this is different threshold values. Currently you can't see, but let's see this over this example. So we start with threshold 0. That means we are predicting everyone as a responder. As I mentioned, I am predicting you all as a responder. So that means we have a line here. Everything above this line will be predicted as a responder, as a yes case. And if I predict everyone as a yes case here, I'm going to cover all yes cases correctly. So these are all true positives. But if I predict everyone as a yes, then I'm going to make mistakes for all of these no, and this will be all false positives. I raise the alarm for these cases. True positive rate would be 1 since we covered all of the yes cases, but false positive rate would be also 1. I couldn't catch any of the non-responders. I predict everyone as a responder. So both cases are 1. When we achieve very high recall rate, we are making lots of mistakes. So now let's say we increase the threshold. We increase the threshold to 0.3. So anything greater than or equal to 0.3 will be predicted as yes, and less than 0.3 will be predicted as no. Now I have, compared to the previous one, I have less yes predictions, but still I catch all of those yes cases. So these are all actual responders. Since I predict everyone as a yes case, I catch all of them. True positive rate is still 1. But now I exclude this particular customer here. This is predicted as no, and it was actually no. So I have 1 true negative. So that means I am making 1 less false positive error. And false positive rate, so this is a false positive. It was no, but we predict as a yes, false positive. It is no, we predict as yes, false positive. So we have 3 false positives out of all 4 no cases. So false positive rate is 0.75. Okay. So as we move the threshold, our yes predictions is going to decrease since we will make less yes predictions. This will help us to decrease our false positive error rate. Since we are predicting less customer as a responder, we will make less mistakes, but at the same time, we can miss actual responders since we will make less yes predictions. So let's see another example. If we have a threshold 0.4, all of these will be predicted as yes, and these will be predicted as no. Now we cover this yes case, so these are all true positives, true positive, true positive. So still, by predicting everyone with the threshold 0.4, yes, we can cover all yes cases, and still our true positive rate is 1. Now we are making less yes predictions since these will be predicted as no, and we are correct in both of them, so these are true negatives. And for the false positives, we predict as a yes, but this was a no case, false positive. We predict as a yes, this was a no, false positive. So we have 2 false positives out of 4 actual no cases. So overall false positive rate drops to 0.5. Okay, so idea is the same. As we move up, when we use 0.6, we have less yes predictions. Now we missed this one since we predict this as a no, but it was yes. Now we have a false negative here. So our true positive rate is going to drop, but now false positive rate will improve. So it is going to drop, but that means we are making less false positives. So when we have all of these values, we just put them onto the ROC chart to see the model performance with respect to different thresholds. So true positive rate, the percentage of actual responders identified correctly on the y-axis, and this is the incorrectly identified not responders. Okay, so what we see in here, as I mentioned, if the model closer, here we have, let's say, 3 models, model 1, model 2, and model 3. if the model closer to the upper left corner, that means it's having a more true positive rate. It can identify more true actual responders while making less false positive errors. So let's have a kind of snapshot here, like have a cut on our graph. So what does it tell us? Where model 1, 2, and 3, they all have a false positive error rate as 0.2. Model 1 can identify with the same error, false positive error. Model 1 can identify 80% of responders. Model 2 can identify around, let's say, 62% of the responders. And Model 3 can identify 40% of the responders. Okay? So with the same error rate, we see these models have different recall rates, or they can identify different percentage of true responders. So we can use this ROC chart to compare different models, and closer to the upper left corner, that means model is performing much better. So let me check whether there are any questions. Which line represents the TPR in the figure? Is this figure or? So true positive rate is on the y-axis. These lines represent the model performance. Baseline, I was about to discuss it. This is the random model. So a random model means we randomly classify customers as responder or not responders. So assume that this company is sending marketing promotions randomly. So they don't use any machine learning model. They just randomly select customers to send the marketing promotion. And this is the performance of the random model. It goes through the diagonal line. That means with the false positive error rate 0.2, we can identify, if we use the random model, we can identify 20% of actual responders. And for a good model, definitely it should be better than the random model. But when you compare different models, closer to the upper left corner, model is much better since it can identify more responders with the less error. So another measure we can obtain from a ROC chart is the area under curve score. So this ROC chart will be automatically actually plotted by using functions in Python, and you would be able to compare several models, and it can return the area under curve score. So this is directly related to the ROC chart. It's basically the area covered by the model under the line. The reason why we have this area under curve score is that, let's say we have another model, and if I go back here, we see models are separated from each other. So we can easily see this green line is much better than the rest. But you may have a model where it can have this type of structure. So initially it is worse, but later it is much better. Or you may have another model. Let's have it as a purple. It is much better, but later it is very close to the random model. So they can be overlapping. And in that case, it may not be easier to identify which model is better. So for that, we use area under curve score. And this score is between 0 and 1. And it shows overall how robust your model is with respect to different thresholds. It returns only one value. If it is close to 1, that means the model is great, perfect. If it is close to 0, that means it is really, really bad. And random model here is a area under curve score 0.5. So for a model to perform better, it should at least, area under curve score should be at least 0.5, which is actually better than the random model. So we will also obtain this value when we compare different models. Higher the area under curve score will help us to see how the model performs with respect to others. Okay, so one last measure and then I will conclude the lecture for today. This is cumulative gain chart, and this is mainly used to explain the results to the managers or to the people who doesn't have a background on, let's say, data science. This is more discussed in business terminology. But on the other hand, if you consider area under curve score or ROC chart, this is more technical, requires more technical knowledge. So cumulative gain chart, evaluate the model's capability, again, identifying a particular outcome like responders. As I mentioned, we will be always focusing on one particular outcome, like cancer, fraudulent activities, responders, or turners. And gain chart can return the outcome based on, or model performance based on the outcome of interest. So what we do is in the ROC chart, we order the probabilities from highest to lowest, and then we use these probabilities to target the customers. So what do I mean? Let's say this is from the previous slides. The responder case, this is our prediction probabilities, and we order these probabilities from most likely to least likely. So this customer, let's go 1, 2, 3, and 4. So fourth one has the prediction probability 0.96. So there's a very high chance this customer is going to respond to the campaign when we offer them. Then the first customer has a chance to respond 0.7. Second customer has a chance to respond 0.47. And third customer is going to respond to the campaign with probability 0.38. So we order from highest to lowest. The reason is you would like to focus on the customers who will respond to your campaign, right? You don't want to focus on the customers who are not interested in. And then we start to target from this. So we send the promotion to the fourth one, then we first one, second one, and third one. So we start by focusing on the highest probability to the lowest probability. So on the x-axis here, we have the percentage of customers targeted based on their prediction probabilities. So 20% means I targeted the top 20% who are interested in with the marketing campaign based on my prediction model. And this is 100, that means we actually target all of the customers. We sent the promotion or campaign to all of the customers. So this is help us to identify customers who would be interested in or the outcome of interest. And we can use this chart to see what would be the success of the model. For instance, what would be the impact of targeting 30% of the customers? So from our chart, this is 30%. If we check the 30% here, this will tell us what is the actual churners or responders based on the problem we are tackling, we can capture with the model. So what does it tell us? If we target the first top 30%, we can actually identify 50% of the churners or 50% of the responders based on the example or business context. And let's say as a business, you have a limited budget. You know that you can at most identify or at most target the top 30. So what is this model is doing in that case? Is there any alternative model it can achieve better performance with the same amount of customers we are targeting? So let's say we have another model like this. For both models, if we only target the top 30%, while one of them can help us to catch 50% of the churners, the other one can help us to catch 70%. So which model to choose? Definitely, you will focus on the red one since it can help you to, using the same budget, it can help you to identify more customers. So we will discuss these cases during our workshop next week, but please check the chapters I posted on the module page. There are 2 chapters on the book. Those chapters actually explain these topics with examples, and it can give you more clarity on the different evaluation techniques. And next Monday or Tuesday, based on your workshop groups, we will see applications of these evaluation techniques. So thank you, everyone. If you have any questions, please feel free to post. I would be happy to answer. I know we cover lots of different techniques, but please take your time, read those chapters from the book, go over the slides, These topics are not that difficult. It just requires some adaptation and reading, and also seeing examples. Definitely it helps. No questions at all? I don't see any questions. If you don't have any questions, I can conclude the lecture. I will stay for 5 more minutes. If you have anything, please feel free to post on the chat. Otherwise, I will see you next Monday or Tuesday based on your workshop group. Thank you all. Thank you. Let me stop the recording.